Let's take a look at esters and carboxylic acids. So we know something about esters and carboxylic acids versus, say, a ketone and an aldehyde. Esters and carboxylic acids can both do resonance. And what's that going to do to this carbon and the carbonyl? Because both of these can do resonance, it's going to make this carbon and the carbonyl that much less reactive. Right? We're going to move electrons here, and it's going to make this less delta plus because we're pushing electrons there. Also with carboxylic acids, you got to be careful because, of course, what is a carboxylic acid? It's an acid, right? It has OHs, it has an OH. Well, that means those really good nucleophiles, carbanion, C minus, H minus, they react a lot of times with this first, right? So there's a couple different things that'll happen here. So with a Grignards will react with esters, and they're going to add twice. They're going to add, they're usually be an excess, and they'll add twice. And we'll end up with an alcohol and a new alcohol with a Grignard added twice. So in this case, two H's have come from the aluminum hydride, right? So there's two H's there, and then the H plus. So there's 4 hydrides available, so we don't need to say excess here. So there's 4 available, and then of course it'd be excess H plus, and we get the alcohols from there. Now this becomes even more complicated when you actually look at carboxylic acid, because carboxylic acid now is an acid. So if you have really strong nucleophiles, like a Grignard, they're not compatible. So what's going to happen here? So I go A, the same type of reagents as before. What's going to happen here actually, this is step 1, then step 2, it's H plus. The Grignard is actually going to react with the H first. It's going to go like this and take that hydrogen, right? It's going to act like a base and just deprotonate that. And you're going to get after the first step, right? You just did a deprotonation. You're going to get O minus plus, right? A hydrogen here to go along with the ones that I hadn't drawn in before. And then in the second step, when you protonate, you're just going to, right there. So you're actually going to get back the starting material. And you're going to basically protonate whatever Grignard you have. So that C minus, you're going to replace that magnesium carbon bond with a carbon hydrogen bond. So you got to be careful which kind of things you react your Grignard with. Right? You got to be careful what you react your Grignard with. So in this case, right, anytime there's OHs or there's an acid around, Grignard reagents won't work. Right? So be careful with this. This is a carboxylic acid first. Acid first. Again, the same situation holds for part B. So if we use borohydride down here, not reactive enough. This is not that, right? Same reason up here. This carbon is not very reactive. This borohydride is just not that reactive. So it's not going to probably react there at all. Now, the neat thing is, or the more complicated one, lithium aluminum hydride does react. And that's a more complicated mechanism that I'll show in more detail now. All right, so lithium aluminum hydride, so I have it drawn on the Lewis structure, carboxylic acid. The aluminum, of course, has a negative charge, but that doesn't mean that's where the electron density is actually at. This is the Lewis dot structure lying to us. So the H's are really holding the electron density. So what's going to happen first? The H is going to react to the acid part. So the hydrogen is going to react right there with the carboxylic acid. And that's going to make the carboxylate, LiAlH4. And we also just made H gas, which of course will leave the system. So now, this is very similar to what happens with a Grignard, right? Grignard, we could say, you think this would stop. And in the Grignard reaction, it does stop. But with the lithium hydride, it doesn't. It keeps actually reacting now. So next step. All right, so the next step, now that we have this, we've deprotonated. And actually get to something like this. Actually, there's a couple errors that are going to happen here. So we start with our nucleophile. It's going to react with the electropositive aluminum. At the same time, the hydrogen is going to go back to that carboxylic acid and kick up the electrons, doing the addition that way. You could also draw this stepwise, which I would think would be okay. So I'll draw this stepwise over here. So the same thing, it's just going to take one more step to do. So showing the stepwise version, the negatively charged oxygen reacts with the aluminum. Right, the positively charged, or the aluminum, it's a metal, that's empty spot there. So now we have this again with the aluminum with the negative charge. So you've seen this before. So this is of course the stepwise. So we did this exact same thing before with 3 arrows over here. 1, 2, 3. Here we do 1. Get to this kind of complex like we had before over here. And now we do that simple addition. So now it's an intramolecular addition. An H on the aluminum reacts with the carbon and the carbonyl, kicks that up. Do that addition step. Again, this is very similar. Negative charge on the aluminum, but of course the hydrogens have a lot of the electron density. And that same thing gets us here to this exact same intermediate. And this should look familiar to you. You have a tetrahedral intermediate, we went from sp2 to sp3. To have a tetrahedral intermediate, you ask yourself, do I have any good leaving groups? And actually, this is a good leaving group. So the electrons will come down, do an elimination, and kick that out. We actually end up with is an aldehyde and this aluminum oxide. All right? And this can be used to keep reacting. And essentially, you should know aldehydes are more reactive than carboxylic acids. So as soon as you make this aldehyde, this lithium aluminum hydride is going to keep reacting with it. And you can see that electrons will go here, and then the H will come there, kick that up, right? Or you could, at this point, you could just say, okay, now it's just going to be like H minus. Right? So you do need to know this mechanism for lithium aluminum hydride carboxylic acids. But the second part, you don't really need to know. But you should recognize, first step's deprotonation, you're going to get a gas. Aluminum complexes with the oxygen complex with aluminum. Either can be all in one step or stepwise. Get tetrahedral intermediate. You break down the tetrahedral intermediate. You get an aldehyde, and then that'll keep reacting until you get the alcohol, the final product. This mechanism is also detailed in workshop 2 at the top, so you can go through and see that as well there to practice.